Thank you so much for having me here. So I'm going to be speaking about Kostant-Kumar modules, which are certain modules of our Kac-Moody Lie algebras. So it's a bit of representation theory, but it uses a lot of combinatorial tools. And then we're going to see some applications. So I'll just quickly describe the setup. We are going to work with a symmetrizable Kac-Moody Lie algebra over C. And we know it has this triangular decomposition, and B, which is H plus N plus, is its Borel subalgebra. The simple roots of G we will denote by alpha I, and the set of roots by delta, which can be partitioned into positive and negative roots. And the set of weights we will denote by P, and the set of dominant weights by P plus. For dominant weight lambda, we can always define this module V lambda, which is the irreducible integrable module of highest weight lambda. So the object of study, Kostant-Kumar modules, are submodules of a tensor product of two highest weight modules, V lambda and V mu. Now inside V lambda, we have a vector of weight lambda, and inside V mu, we have a vector of weight VW mu, where W is an element of the while group. So the submodule of the tensor product, which is generated by this single vector, is known as the Kostant-Kumar module. So it depends on lambda, W, and mu. A related object is the de Maizière module. So a de Maizière module is a UB submodule of the highest weight module V mu, where it is generated by a vector VW mu of weight W mu, but it's a UB submodule, not a UG module. So in the finite dimensional semi-simple case, the entire tensor product itself is a Kostant-Kumar module, because if you take W to be the longest element of the while group, you recover the entire tensor product. And the highest weight component, V lambda plus mu, is also a Kostant-Kumar module if you take W to be the identity. Also, a useful tool is the Shapovalov form. So on a highest weight integrable module, you have an inner product form with the property that if you have X and Y in a product and you have G acting on the first component X, then you can move it to the second component by acting by this antilinear automorphism. So an element, if you have an element of UN plus acting on the first component, you can move it to the second component, but it becomes a UN minus element. And the weight spaces are actually orthogonal with respect to this inner product form. This form is unique up to scaling, and any module in category O is a direct sum of highest weight modules. So on each of the components, we can define this Shapovalov form. But because on each of the components, you can choose different scaling, the form is no longer unique. So here, since we're dealing with tensor products, I'm going to fix a canonical choice of the Shapovalov form, where it's just going to be multiplication of the Shapovalov forms on each component. So the first question that I want to ask is, we have the submodule of the tensor product, a UG submodule of the tensor product. How does it break down into irreducibles? And the following result is due to PRV and independently due to Kostant, that this space B, which is defined as vectors from V mu of this weight nu minus lambda, which are killed by this power lambda alpha I check plus 1 of EI. If you take this space, then the dimension of this space gives you the multiplicity of V nu inside the tensor product. So this dimension of D is equal to C lambda nu. This is called the Littlewood-Richardson coefficient. And on the crystal side, you also have an analogous result due to Littleman and also due to Kashiwara, that if you take, so this is a crystal theoretic or path theoretic characterization of this, which are equivalent. So if you take all LS paths of shape nu, such that the weight of the path is nu minus lambda, which are killed by this appropriate power of the path operator, then this number of paths will give you the Littlewood-Richardson coefficient. So the first thing we did was, using Kashiwara's global basis, we extended this to all symmetrizable Kac-Moody Lie algebras. By this we mean, so the PRV result was only for finite dimensional semi-simple Lie algebra, the proof that they gave. So, but we used Littleman's result and we extended it to all symmetrizable Kac-Moody Lie algebras. An alternative proof of this we later discovered was given by Samuel Gerards and Shravan-Kumar, who they used a different limiting sort of argument. So this result is already known for the entire tensor product. Is there anything similar for Kostant-Kumar modules? And on the path theoretic or crystal theoretic side, there is, due to Anthony Joseph, which is, if you take all paths in the de paths set, which are LS paths of the shape mu with initial direction less than or equal to W, and you set the weight of the path to be nu minus lambda, again killed by this appropriate power of the path operator, then the cardinality of this set gives you the multiplicity of the irreducible V nu inside the Kostant-Kumar module now. Instead of the entire tensor product, it tells you how many times V nu occurs in the decomposition of the Kostant-Kumar module. So sometimes these C, lambda, mu, nu, W are also known as refined Littlewood-Richardson coefficients. So now this is on the path theoretic side. We asked if there's anything we can say on the module theoretic side. And this is the first result, that if you take the space D and you project it via the Shapovalov form with respect to the Shapovalov form onto the de Maizière, then the dimension of the image of the space D gives you the refined Littlewood-Richardson coefficients. So if you look at the result from Joseph, it kind of suggests that since they're taking paths from the de Maizière crystal, maybe we should just take vectors from the de Maizière module, which are of the appropriate weight and killed by the appropriate power of EI. But that space turns out to not have the correct multiplicity. So instead of taking the intersection of D with the de Maizière, what you have to do is project the de Maizière onto the, project the space D onto the de Maizière. That is what gives you the correct multiplicity. And now, the proof is crucially uses the fact that the Shapovalov form, when you have a projection from a cyclic UG module to a cyclic UB module generated by the same vector, then this projection becomes injective. The second question that we asked was, we have these Kostant-Kumar modules. We know that this is generated by a single vector because it's by definition. So what is its annihilator? Can we give relations for this generator? And so we tried the obvious candidate, which was E alpha to the power P alpha and F alpha to the power P alpha dash plus 1 and the H action, where P alpha and P alpha dash are the highest powers of E alpha and F alpha that can act on the vector without killing it. So this comes from, so this guess comes from looking at annihilator of the entire tensor product, which was known, which is generated by V lambda tensor V W naught mu, from looking at the annihilator of V lambda or any vector V lambda inside capital V lambda, and the de Maizière relations. If you look at all of these relations, they never have any mixed terms in them. They only have E alpha to some power, F alpha to some power, but never any mixed terms. And finding these powers is not very difficult. So for example, this E alpha will only act on the second component because V alpha, because V lambda is the highest weight vector. So E alpha will kill it and will only act on the second component. And from there on, you can see that the value of P alpha should be this and the value of Q alpha should be this. So it turns out that our guess was correct, and the annihilator of this vector is exactly E alpha to those powers, F alpha to those powers, and the H action, and then E alpha for imaginary positive roots alpha. And of course, there can be multiple E alphas for because there might be multiple the dimension of the space G alpha, where alpha is imaginary, might not be one dimensional. So but it can so it has no F counter counterpart, because F can act F alpha for alpha imaginary can act however many times. So the proof has two main ingredients. First is this isomorphism. Hom G from the Kostant-Kumar to V nu is isomorphic to Hom B from V lambda tensor V W mu to V nu. So this was proved by Kumar for finite dimensional semi-simple Lie algebras, and we used Joseph's and Polo and Matthews' excellent filtrations to give a result in the case of the symmetric Kac-Moody Lie algebras. The second ingredient is the generators and relations description of Ramsey module. This was proved by Joseph in the finite dimensional case, and Matthew for symmetrizable Kac-Moody Lie algebra, and Polo for characteristic P. And Matthew's proof is based on Polo's proof. Also, the same Kostant-Kumar module can be generated by different vectors. So if you act by an element of the while group on the module, by which I mean these Ri operators. So if Si is a simple reflection, then Riv is defined like this. So for if you write W as a reduced word, we can define correspondingly an operator for that word. And when it acts on the module, it changes the weights by that element of the while group. Now, elements like this will also generate the same Kostant-Kumar module. And to get relations for that, we just need to observe that the smallest power of E alpha, which kills this tau V acting on V, is the smallest power of E tau inverse alpha, which kills V. So this is like a twisted version of the generator, and you will get some twisted relations. Okay, so for the application, we have this sure positivity type result. So the characters of highest weight modules, they correspond to different symmetric functions, and particularly to sure polynomials in type A. And a surjective homomorphism from V lambda 1 tensor V mu 1 to V lambda 2 tensor V mu 2 is a necessary condition for a sure positivity result of functions of the form S lambda 1 S mu 1 minus S lambda 2 S mu 2. But this is because one has character, because saying that this is sure positive means that the second module is actually contained inside the first. That's why their difference is actually positive sure polynomials themselves, which are exactly the irreducibles which occur in the first but don't occur in the second. And there is another necessary condition for sure positivity, which is given any cyclic module UG V mu, where V mu is the vector of weight mu for some category O integrable representation of G, the highest weights occurring in the decomposition of UG V mu are dominant weights occurring in UB V mu. So for our setup, it means that if we have two Kostant-Kumar modules and there is a surjective homomorphism between them, then that means that lambda 2 plus W2 mu 2's dominant conjugate has to be greater than or equal to the dominant conjugate of lambda 1 plus W1 mu 1. So using our generators and relations description, we have a sure positivity result, which is a generalization of Matthew's result for the full tensor product, which is just giving conditions for when there will be surjective homomorphisms between these two Kostant-Kumar modules, but special kind of homomorphisms which send this generating vector to a generating vector of this kind. And that these conditions just correspond to saying that the annihilator of one vector should be contained inside the annihilator of the second vector in UG. And this is how we discover these. We recover these conditions. So an example of this is if you take rho to be identity, I mean you don't twist the generator, and you take W1 to be equal to W2 to be equal to W, then there is a surjection which sends this to this if and only if lambda1 minus lambda2 is equal to W of mu2 minus mu1, which is a dominant weight. And another condition for sure positivity is saying that the highest weight of occurring in the first Kostant-Kumar module is greater than or equal to the highest weight occurring in the second Kostant-Kumar module. So for the full tensor product and even for the Kostant-Kumar module, because these weights will always occur in a Kostant-Kumar module, is that lambda1 plus mu1 is greater than or equal to lambda2 plus mu2. But equality in this condition has been studied for product differences of products like S lambda, S mu minus. Yeah. So equality in this case has been studied quite extensively by Lamposnikov, Pilyavsky, and Charya Fourier Sasaki. But in those conditions, it seems to be kind of difficult because even for this function sort, which is a maximal element in many of these partial orders, there is no homomorphism which sends a generator of this kind to a generator of this kind. And these are the references. Thank you so much.